Hello everyone. Today I am going to present our paper Unified Pre-Training for Program Understanding and Generation. This work is a collaboration between Columbia University, New York and University of California, Los Angeles. I am Saikat Chakraborty presenting today. Before moving on to the details of this paper, let us look at some of the example NLP applications in software engineering. First application is code summarization, where the input is a piece of code and the expected output is the summary of the input code. In this task, the main goal is to translate the programming language sentence into a natural language sentence. Second example application is code translation, where the input is in one programming language. For instance, in this case, the input is a Python code and the output is the same code implemented in another programming language, for example, in Java. In this task, our main goal is to translate a Python sentence to a Java sentence. Last but not the least, our third example task is code generation, where the input is a natural language description of a code and the output is corresponding code in programming language. For example, in this example shown here, the goal is to translate the natural language sentence to the corresponding sentence in Python. If we notice closely, we can see that the tasks we have seen so far are all generative tasks. In fact, a lot of natural language processing tasks used in software engineering are generative tasks. Now let us assume that there is a hypothetical system which can solve all these tasks. Let us see what should we expect from such a system. Let us consider the program generation task. If we want to design a system that can successfully synthesize any code from a natural language, or at least this code from the given natural language sentence, it must understand that the first element of the tuple is accessed by .get0 in Java and like an array index in Python. If we note carefully, we can see that these information are related to the API semantics of the programming language. Thus, the system able to do this translation task must be able to understand the API semantics of the programming languages. Also, if we consider the code translation task from Python to Java, at first glance, it might look like very straightforward. In fact, in theory, translation between two Turing-complete programming languages should be deterministic. But due to the widespread use of different libraries and APIs in software development, such deterministic translation may not always be possible. For instance, in this example, while translating this Java code to the Python code, the tool or the model must understand that the arrays.sort Java works similarly to the sorted API in Python. Also, the model needs to understand that instantiating a comparator object in Java is semantically similar to the lambda expression in Python. Such analogies depend on how these APIs are implemented, and these analogies are beyond the syntactic and semantic properties of the programming language. Now let us look at how a tool can perform all these tasks. For this task, a tool that can perform this task must learn about the token formation, learn about the syntax, learn about the data flow in the code, learn about the structure of the code, and finally, the tool needs to reason about all these things to perform a specific task. In another word, first 4 tasks are about learning the language, and the last task is about learning the task. In general terms, for a model that transforms an input to an output, there are actually 2 subtasks in place. First, the language model, then the task model. Though these two parts of the model are not explicit and often these parts interact with each other, we can conceptually subdivide any model in this way. These two models are jointly trained for learning a specific task. However, since the language does not depend on any particular task, and since there are billions of lines of code in open source repositories like GitHub and Stack Overflow, we can pre-train such a language model using these data. Now let us see what properties should a language model have. The language model should properly understand the input. If the input is a code, it should understand the long-range dependencies in the code. It should generate syntactically correct code. It should generate logically correct code. And finally, it should generate semantically correct code. As we can see, the model must be able to understand and must be able to generate source code to be useful in any software engineering task. With that spirit, we designed PLBART, a pre-trained model for simultaneously understanding and generating source code. PLBART consists of a bidirectional encoder and an autorecursive left-to-right decoder. The encoder and the decoder is pre-trained simultaneously. We can use such a pre-trained model directly for downstream sequence-to-sequence tasks. We use multilingual denoising autoencoding for pre-training PLBART. We provide the encoder with noise-induced input and expect the decoder to generate noise-removed version of the input. We train PLBART using a large collection of source code and natural language, including 470 million Java code, 210 million Python code, and 47 million Stack Overflow posts. We use three different noising strategies for denoising tasks. First, we use token masking, where we randomly mask out some of the tokens. Second, we use token deletion, where we delete randomly some tokens from the input. And third, we use token infilling, where we mask out a subsequence of tokens. We fine-tuned and evaluated PLBART on a large variety of software engineering tasks, including both understanding and generative tasks. Among the generative tasks, we evaluate PLBART on code summarization, code generation, and two different types of code translation. As for the understanding task, we evaluated PLBART on vulnerability detection and code clone detection. Here we see the result of code summarization, where except for one language, PLBART outperforms all the existing baselines in all other languages. Note that we only use Java and Python for pre-training PLBART. In pre-training stage, PLBART does not see other languages like Ruby, JavaScript, Go, etc. However, we believe due to the multilingual nature of PLBART, it learns beyond the syntax of any particular language. Here we see the code generation result. In terms of blue and code blue, PLBART outperforms existing baselines. However, in terms of the exact match, PLBART does not. To understand that even further, let us look at an example for code generation. Given this input in natural language, PLBART is expected to generate this code. However, PLBART generates this code, which is obviously not an exact match. However, if we look closely, we can see that these two pieces of code are semantically equivalent. The generated code by PLBART is semantically equivalent to what was expected. PLBART generates a large number of such semantically equivalent functions. Thus, even though the exact match is lower than other baselines, blue and code blue scores are higher than the baselines. Here we see the code translation result. We evaluated PLBART on two different settings, from translating from Java to C# and vice versa. In both cases, PLBART outperforms all the existing baselines. Here is an example of code translation using PLBART. This C# code is correctly translated to the Java code by PLBART. There are some more subtle and interesting example to note here. In the input code, a collection of is iterated by a for each loop. However, there is no such thing as for each in Java. The way to iterate the collection in Java is through an iterator. And as we can see, PLBART exactly does that. Another interesting thing to note here, the custom of writing identifier in both C# and Java is camel casing. However, in C#, developers usually start the identifier with a capital letter. In Java, however, the same identifier is usually started with a small letter. Due to the prevalence of such pattern in pre-training data, PLBART is able to learn even such subtle features from the language. We designed PLBART in a way that is simple yet effective. We believe that PLBART can be very useful in other software engineering related tasks. To facilitate further use of PLBART, we released our pre-trained model code and data in these links. I thank you all for listening to the talk today, and I will be happy to answer any question.